I got a warning here that we are live on YouTube.
Okay, yeah, good start. So,
okay. Just adjusting it.
Okay, yeah. Welcome everybody to this QPequi talk. We are now live on YouTube. Today we have Professor Fernando Parisio from the Federal University of Pernambuco. Sorry, that was my audio. And he's going to talk with us today about quantum resources. Please, Fernando, you can start when you're ready. Thank you so much for accepting our invitation.
Okay. Yes, it's a great pleasure to talk about things that we like to people that is probably interested. So I thank you for the invitation, and also Lucas. And yes, there is this terminology, the resource in the title, but in fact, I'm not going to use any deep facts of the formal resource theory, but it is still about quantum resource, so the title is justified. Okay. Oops, I'm not, okay. My keyboard is not working, but the mouse is working, so. Okay, the fact is that it's not a privilege of quantum mechanics that several resources do not present a trivial behavior when you consider an arbitrary number of elementary objects. So you have this example, the assembly line production discovered by Henry Ford, in which, what was the great thing about this? It is here, the fact that the cost of producing n cars is smaller, or maybe smaller than n times the cost to produce one car. Okay, so what Ford discovered was the non-additivity of the cost of producing cars. Okay, so we are not interested in cars. We are more interested in this kind of industry. So you know that several tasks in quantum mechanics of either practical or fundamental importance require more than one state. In general, you need a pack of identically prepared states to execute some of the tasks, okay? And then the question is how to calculate the cost or the coherence of this pack of states, or the entanglement or non-locality, whatever, okay? So we will be talking about an arbitrary, sometimes I will call it entanglement just for definiteness, but there is no specificity in the theory, all right? So we will be generally speaking about a figure of merit that we want to determine for a number of identically prepared states, all right? So this is about, this is the topic of this talk. Okay, what usually, what are we able to do? We can calculate for these quantities for one copy of the state, perhaps for two copies of the state. And sometimes we know how to calculate it for an infinite number of states. But usually there is this huge gray zone for which we cannot, at least we don't know how to calculate. Okay, maybe you can calculate for 3 copies, 4 copies, or even for n copies for a specific figure of merit and a specific state. But generally speaking, it is very hard to determine how to scale these quantities, okay? So, and this gray square here is important because several times we need to know what are the resources involved in the pack of 10 states, 20 states, okay? And we may not know presently. Why is it so hard? Because I give two arbitrary or more or less arbitrary examples here. Why is it so hard? Because it involves the definitions usually involve optimizations that take place in large Hilbert space, especially when you consider several copies of the states. You increase exponentially the dimension of the Hilbert space. Okay, so for instance, entanglement of formation, you have to make optimizations over all possible realizations, ensemble realizations of that state. Distillable entanglement, you have a soup, you have a nymph, and this is hell to calculate in practice. So, for instance, you can calculate the concurrence for 2 qubits, but the entanglement of formation for 3 qubits or an arbitrary number of qubits or for qubits, it's not no in general, okay? So it is hard to calculate these quantities, but not always, okay? You do have some measures that are very simple. For instance, the simplest case is the case of additive measures. So you have, for instance, for entanglement, you have squashed entanglement, you have the logarithmic negativity, which behave like this. The entanglement of n copies is simply the entanglement of a single copy times n. This is the simplest case. But this is not common. This is unusual. Okay. So, but let's use this example to make a small change in notation, which will bring, as you will see, a change in perspective. Okay, I will say that I will rewrite this relation like this. I'll say that, okay, if the entanglement of a single copy determines in a very simple way the entanglement of an arbitrary number of copies, I will call this, I will calculate this in advance. I will get this real number, and which is here, and I will consider this my variable. Okay, so in this case, I will represent this function, which is defined on whose domain is a huge Hilbert space. I will rewrite it as a function whose domain is the real set. Okay. Okay. Of course, Fernando, this is trivial. Oi.
Fernando, can I ask a question?
Yeah, sure.
So am I allowed to coherently act on different copies of the system, or they are completely independent?
No, they are completely independent.
Okay.
I'm talking about a pack of non-interacting equal states.
Okay.
Right? Okay. So, okay. So this is just a change in notation. I will represent this guy with this notation, a real function of a real argument with this discrete index identify the number of copies. This is so trivial that it's just a change in notation for now. Okay, this is the simplest case. Let's go to a complicated case just to make a contrast. A complicated case is that for instance, for some measures, And some states, you have this interesting phenomenon of superactivation, which is which amounts to the fact that sometimes you can choose a quantity, a figure of merit, and a state, and you get that it gives you 0 resource. Although if you consider 2 copies or 3 copies or an arbitrary number of copies, you suddenly get a number that is non-zero, okay? So in this case, it is quite clear that the entanglement of an arbitrary number of copies could never be determined by the entanglement of a single copy because it is 0. So of course, this kind of behavior is very limited, is very restricted, right? So just to give you a contrast, superactivation could never be characterized in that way, okay? So what's the idea of this work? Why not considering the case? Okay, the additive case is the simplest one. You have a single state determining the way the quantity behaves for an arbitrary number of states. What if you find some quantity for which this is not enough, but if you know the entanglement of 1 copy and the entanglement or coherence or whatever of 2 copies, you might be able to determine the quantity for n copies. So I am using that way of looking at additive measures to look for some more general behaviors, which are still more easy to cope with, okay? So why not look for measures that can be seen as functions of 2 real variables that give the entanglement of 1 copy and 2 copies? Is that possible? We will see. So the general idea is to consider that the figure of merit you want to calculate is a function of q real numbers, which are exactly the same quantity for a smaller number of copies, okay? So for instance, you may show that the entanglement for an arbitrary number of copies is determined by the entanglement of a single copy, 3 copies, and 9 copies, for instance, okay? So this is the general idea. It is not, I'm not saying that every figure of merit can be put in this format, but this is much more general than additivity, for instance, okay? The first question that arises, okay, is every function that I can imagine of q variables a valid, possibly valid candidate, okay? The answer is no, because there is a very simple consistency condition that you must take into account. Well, when you calculate this, if you are able to, directly from the definitions, that complicated definitions, you do not have to worry about respecting the structure of tensor product, because it is built in. You are calculating things using quantum states, and quantum states respect the structure of tensor product. However, if you are to take this kind of shortcut, you have to check whether or not this function is in accordance with the structure of tensor product in a very simple way. Okay, so this is a tautologic slide, right? But because it is a very simple condition, I'm just saying that I can take this n tensorings of this state and write it as 2 tensorings of these 2 states, or 4 tensorings of these 4 states, and so on. Of course, I am implicitly assuming that this n is a power of 2, because otherwise I can get 5/2 here, which, well, maybe we can mathematically define this, but it does not represent a physical state of a system, all right? So I need to guarantee that this is an integer. So in this example, I am saying that I am assuming that n is 2 to the n, this lowercase n. Generally speaking, I will represent this kind of relation like this. Rho to n is equals to sigma to n over k, with sigma equals to k tensor rings of rho. It's a triviality. Also, it's going to be useful to name the set of all integer powers of an arbitrary integer a as PA, okay? So this is a to 0, a to 1, a to 2, and so on. Okay, what is the condition? Look, if I am saying that, if I'm saying that this state is identically equals to this state, any quantity calculated over this state must equal the quantity calculated to this state, because it is the same state. Okay, so this is what I am saying here. And here I am back to the case where I have a single variable because it is simpler to present the reasoning. Then we go back to the general case. So remember that I am using this notation here, okay? The quantity for n copies is given by this, and this is a real number that I am calling E1, okay? So if I use this notation here, in this side, the right-hand side, I get simply this. Can you see my arrow?
Yeah.
Okay. So you get this, right? In the left hand side. In the right-hand side, you get this. This is the entanglement of n over k copies of sigma here, but then as a function of the entanglement of sigma. But the entanglement of sigma, since sigma is this, is EKU1. So this is very simple, but it is a mathematically non-trivial relation. I must guarantee that this relation is obeyed in order to have the tensor product respected by the function. Okay, let me give you an example. Suppose I come here and say, well, I found a quantity that quantifies the entanglement or the coherence, whatever, for n copies in terms of the entanglement of one copy, and the function is this, n times a number to n minus 1 times E1, okay? For n equals to 0, we get 0. For n equals to 1, we get 1. The exponent here is 0, so this is 1. So we get E1 as we should. So it looks reasonable, okay? It's almost, I mean, if for 2 copies, we would have 2 lambda E1. So it's something simple, but it could not be right because it doesn't satisfy that simple relation. So this can never represent a figure of merit regarding n copies of a state whose quantity for one copy is E1. Okay, so this gives you an example that simple condition, this simple condition here, constrains quite strongly, as we will see, the functional forms that are allowed. Okay, let me just give you...
Fernando.
Yes?
So it looks to me like this constraint of yours is more like a necessary condition on additivity of this quantity E.
No. No, it's not to additivity. It's
because in case it is additive, this would obviously hold, right?
Yes, this would obviously hold, but it's much more general. I will present to you a quantity that is not additive at all, which satisfies the condition. Okay, so it's much more general. Okay.
Okay.
There are a bunch of non-linear dependencies that satisfy this condition. You will see in a few slides. Okay. Before giving an example, it's the next slide, the measure of coherence. But I just would like to present a general result, just to let you know that there is also a constraint for the general case where you have Q variables, and it is a little bit ugly, but it's not hard to apply. I will also give you an example, all right? So do not bother with the details here. It's just for you to know that we can also derive a constraint in the general case based on the same reasoning on tensor products. Okay, let's
just another question then.
Okay.
So what can you really learn from your previous example with the lambda?
Yeah, that it's just an illustration that it's not any old function that could be allowed as a valid measure. I mean, you could think that, well, I can invent lots of consistent measures of lots of different quantities. Okay, so perhaps that function fits at least one of these quantities. And I'm saying that no, it is impossible because it wouldn't respect the structure of tensor product.
I see now. Okay.
Yeah. See, so it's not possible. You can spend the rest of your life trying to find some definition over quantum states that produce a number and that has that behavior, and I'm telling you that it won't happen. Okay. Okay. That is a constraint, a necessary one. You cannot escape the structure of tensor product. What I'm going to do now to make that condition more operational, to get numbers from that condition, is to make an extra assumption. And in this case, it is an assumption. But you will probably agree with me that it is a mild one. I'm just going to assume that these functions are minimally well behaved around zero resources, meaning that I will assume that these functions do have a Taylor expansion, a Taylor series, a Maclaurin series, because it is around zero, that converges to the value of the function within some finite ball. Okay, so it's not a strong constraint, but a strong condition, but it is a condition. Okay, so let me go back to the case of a single variable, just to illustrate to you how this would work. Okay, now I know that I can make this expansion, okay, of my real valued function, and I have this condition that comes from the structure of tensor product. Then I can use this expansion here with index n. I can use the expansion here with index k, and then I can expand everything with this index. It's a mess, but I can simply collect the terms with the same orders and equate them, and then I get recurrence relations. All right, and I can solve them. So the recurrence relation for the first order terms, the term that is proportional to E1, the recurrence relation that comes from the terms, the square terms, and so on. And I can solve this to get the explicit functional form of any measure that is analytic at the origin and that respects the tensor product. They must have this Taylor expansion. There's no escape. Okay, so what do I need to know? Note that these terms here, D2 and D3, are the coefficients of the expansion for the next quantity. So I have the variable, the value of the entanglement for a single copy, and then the next power is, for instance, 2 copies. Then I must know, even if it is numerically, how the entanglement of 2 copies depends on the entanglement of 1 copy. So I must know these coefficients. If I know, I can determine for an arbitrary number of copies. Okay, and I stopped here because it is too hard. You see that the 3rd order quantity is already ugly, and the 4th order I couldn't find analytically, but I did determine the recurrence relations to all orders. Okay, you can solve them numerically, but the recurrence relations for all orders are calculated. All right. So let me give you an example. Let us consider a very well-known coherence quantifier, which is called the L1 norm of coherence. It was proposed in late 90s. It's quite old already, and it's very simple. You just sum the modulus of all coherences of a density matrix. It's very simple. It's not the squared modulus, because the squared modulus was shown in the same paper. It's a paper by Martin Plenio and 2 other authors. Unfortunately, I do not remember now. It's a physical review letters. And if you put a square here, you mess things. It's not a proper measure of coherence. But if you only sum the modulus, it's a proper measure of coherence. So if you call the coherence of a single copy C, you can show easily that the coherence of 2 copies is given in terms of the coherence of a single copy as 2C plus C squared. Oh, this gives me some hope. And a master's student that he just finished his master's, he showed that the coherence for n copies, arbitrary, is just this. So I am, Matheus, presenting you a one scalable quantity that is not additive at all, but it is a function of the coherence of a single copy, and it is, you can test that condition of scalability, it satisfies. Of course, otherwise it wouldn't respect the structure of tensor product. Okay, so you can now, knowing the coherence of a single copy, you know immediately the coherence of 10, 100, and 1,000 copies. Okay, so this is just an example to illustrate your question. Okay.
Fernando.
Yes, yes.
I were talking about coherences. I mean, between any partition of the system.
No, it is very simple. It is a base-dependent quantity. You choose a basis, and you get the matrix that represents the state in that basis. And then you sum the modulus of all of diagonal terms.
Oh, it's like the total coherence.
Yeah, total coherence. Yes. Okay.
And how the result depends on the basis.
Yes, because for instance,
I see. In terms of coherence of the okay.
It can be always 0. For instance, if you go to the spectral basis, it's 0.
Yeah.
Okay. Yeah. Okay. So this is an example. Let me now give a step, further step by considering, okay, you found an example existing for almost 30 years of one scalable function that is not trivial in the sense that it's not additive. Can you find a more, in a sense, interesting example? So let us go to the case of two scalability. In the case of two scalability, that condition reads like this: E and F, instead of E1 and E2, to simplify the notation, I am using E and F. E is for instance, the entanglement of one copy, F the entanglement of two copies. Or more generally, E is the entanglement of a number of copies, and F is the entanglement of another number of copies, both smaller than n. Okay, and the condition is like this. Oh God, this is in Portuguese. I got distracted. The only Portuguese sentence. So you do the same thing. All right. You also assume analyticity. You expand, collect terms of same order, and you also get recurrence relations, which are more complicated because now you have coupled recurrence relations. I'm not going through the technicalities. I'll just give you one example that I kind of fall in love about because it involves Fibonacci numbers. So for instance, if you show that a measure, arbitrary measure, is too scalable, okay, it depends on for instance, in this case, let us consider 2 to n copies. So we, sorry, we are considering 1, 2, 4, 8, etc. copies, all right? So suppose you know the entanglement of one copy, and then the entanglement of two copies. E is the entanglement of one copy, F is the entanglement of two copies. Now you have to know, even if it is numerically, no problem, how the entanglement, the next entanglement depends on them. The entanglement of two copies depends how they depend on EF. Okay, and this is the first order.
I have, sorry, I have a naive question here.
Okay.
I mean, if I have the entanglement of one single copy, and I assume that I cannot coherently act on different copies, so they are completely independent, entanglement should be additive, no?
No.
What am I missing here?
No. Most of the measures of entanglement are not additive. For instance, entanglement of formation, okay? Entanglement of formation, you are looking for the optimal ensemble realization such that the entanglement of the states that you use adds to a minimum, right? So it has been shown that when you consider two copies, a tensor of two copies.
Oh, I see what you mean, because the Hilbert space of more copies is much bigger.
Yes.
And you can do much better.
Yeah. So it is in this example that I gave, it has been shown that it's subadditive. There are some states that you can, using this fact that you just said, you can show that the entanglement of formation of two copies is less than 2 times the entanglement of formation of one copy in some cases. In some cases, it is additive. Okay. And so it is possible to show when you solve the recurrence relations that the entanglement under these conditions, knowing these coefficients x and y, the entanglement of an arbitrary power, okay, is given by this function where x is this coefficient, ui is here because this q is a ratio of ui square root of x, and these guys are Fibonacci polynomials. The Fibonacci polynomials are defined like this, and you get the Fibonacci numbers whenever the argument is 1. okay? So I got excited about this result and set to look for a quantity that I could test. I was looking for some figure of merit to put these things to test. It is very hard task because since the quantities are hard to calculate, I was not able to find numeric results involving more than 2 or 3 copies. And in this case, I couldn't test what I was saying, right? But then I found this paper after a month of search, okay? I found this paper and this plot caught my eye because I saw 100 copies and the quantity has been calculated numerically for 100 copies. And I said, I can try at least to test my theory. So I'm not going again to go through the details, the technicalities. We can talk later or whenever you want. But this is the quantity that they address in this paper is a kind of distillable entanglement, but it is different. It's not about the number of singlets you can extract asymptotically, but about the dimension of the maximally entangled state that you can extract in a single try, okay? It is a complicated quantity, very complicated, okay? But then there are two instances here. First, they have shown that for this particular Bell family of Bell states, the combination of these two, a statistical combination of these two Bell states, that one-shot distillable entanglement can be, at least in the asymptotically, be calculated analytically, okay? Then I calculated it for 2 arbitrary number of copies, say M and L, and then I showed that that general quantity could be expressed in terms of, I called the one-shot distillable entanglement for L copies, F, the one-shot distillable entanglement for N copies, and then I showed that for N copies, I could write this. Wow. So at least for that family of states, this is a 2 scalable function. Yes, I checked the condition. It is very boring to calculate, but it is perfectly satisfied. It is a 2 scalable function. Okay, this is just a proof of principle because it is useless. You already have the analytical result here. So it's just a proof of principle. Okay, you did this, but they already had the analytical result. Then I go to a second state. This state is a statistical mixture of a maximally entangled states of 2 qubits. Okay, so this is this is a 2 q-treats for d equals to 3 as the numerical example I will address, and then white noise, okay? And in this case, nobody was able to get an analytical expression. And it was for this case that they plot that numeric results for 100 copies, okay? Because they showed that this could be mapped in a linear program that could be solved numerically using Maple, Mathematica, or some of these programs. So specifically, they used 2 entangled Q-treats and a fidelity of 90%. And the quantity involves also a error tolerance that they set to 1 part in 1,000. Okay. Here's the quantity. They have calculated it using that linear program. It is quite complicated. It has superactivation. It is 0 for 1, 2, 3, 4, 5 copies, and then non-zero for 6 copies. Okay. And since I have shown analytically that for another family of states, it would be too scalable, I guess that this would also be the case. Okay, so but my student, Matteo, said, but Parisio, perhaps it is 3 scalable, but I mean, it depends on 1 copy, something square, something 6 copies in this case, and 6 squared. But 1 copy is 0. What's the difference? The point is that if you consider that the mathematical relations for 1 copy and then make it 0, the relations are different. So what I will show, and it's going to be my last slide, is the result of an assumption of 3 scalability, however, with E1 being 0. The one-shot distillable entanglement for 1 copy is 0, for 6 copies is non-zero, and 36 copy is non-zero. So the only data that we used was the entanglement of 6 copies, 36, and 1 copy, 0, right? So this is the relation we get. It's a bit complicated. A is that integer that I consider the powers. So in this case, it's 6, 6 to 0, 6 to 1, 6 squared, and is the number of copies. And this is the entanglement of 6 copies that I got from the plot, the entanglement of 36 copies that I got from the plot. And this is the result, our result. Okay, this function is the dotted line, the dotted curve, and this is that numeric results up to 40. We reproduce the linear program, but we were not able, our computer was not able to go beyond 40. Okay, so the result is quite exciting, and there is no fitting. Okay, of course, I took this result from the numerical data. I took 36 around here, and that's it. I just plugged here and here, and this is the function. In addition, if you calculate the asymptotic, well, this quantity is regularizable. It means that when you take the number of copies going to infinity and divide by n, that is the one-shot distillable entanglement per copy in the asymptotic limit is finite. It doesn't diverge and it doesn't go to 0. So it is this straight line. This is the asymptotic behavior. And when you calculate the asymptotic behavior here, you get this red line, which is 93% of precision. Okay, so we are excited with these results. This last part is not published yet. We are writing the paper, and that's it. Thank you. I'm sorry. I just would like to say that, of course, it would be important to run more numerical tests to go for higher order in the expansions. But mainly, my question that would make this formalism, in fact, very useful would be the following. Okay, you look at that definitions, very complicated with optimizations over complicated Hilbert space. For instance, entanglement of formation or distillable entanglement. You don't know how to calculate that quantities for an arbitrary number of copies. But can you look at that quantities and even without calculating anything explicitly, can you prove scalability? Because if you can, then you can calculate it taking the shortcut. You use your computer to calculate for a few number of copies, and then scalability will do the rest of the work. So this is the important question. Can, at least for some family of the states and for some important definitions, we prove scalability from the definitions. And if this is possible, at least in some cases, I think that this formalism will be useful. If not, it's more like a curiosity. Okay, that's it. Thank you very much.
Thank you so much, Professor Fernando, for your presentation. Do we have any questions?
I have one.
Okay, so go on, Lucas.
Fernando, thanks for the talk, man. It's I found that it's really interesting, and my question is, actually I have two.
Okay.
The first one is, can you extend this formalism to channels? I mean, based on some sort of Choi-Yamilskovsky isomorphism or things like this.
Yes, possibly. In fact, that result that I mentioned to you, that the entanglement of formation is not additive, was demonstrated for channels. And then, because of this relation, it also holds for the entanglement of formation. It's a nature. So I think so, but I didn't give.
Oh, it's a Martin Hastings paper, no?
I think so. Yes. Yes.
Okay, I know the paper.
Yes. Yeah. So I think it is possible, but I didn't work in this direction so far.
And this would be nice because nobody actually knows if I give you two channels. Nobody actually knows when the capacity will be additive or not.
Or not, yes.
And so, even worse question, nobody knows up to when you can break it.
Yes, I would say it's clear that the capacity is not additive, right, from that paper you're mentioning.
Yeah. But I mean, how?
No, it is not additive.
Exactly,
I mean,
exactly. But maybe we can.
We know that classical channels are additive, and we know that quantum channels are not additive. We just don't know when.
How non-additive is the question?
Yeah, exactly. Yeah, and maybe we can try, because that would be my question actually. So I don't know if I understood correctly, but we need to show that in a sense every reasonable measure would be scalable to some order, right? Is that what you're trying to?
No. Because it's more the opposite. If you are describing any quantity with a function of real numbers, it must be scalable. But this does not imply that you define a quantity on Hilbert space and that it will be automatically scalable. In fact, it is not. Because I'm not recalling what is the quantity, but there are quantities that present superactivation for an arbitrarily high number of copies. So you have it's 0 for 1,000 copies and then non-zero for 1,001. So this is in fact a proof that not everything can be put in this pack of scalability, but I see.
So it's totally non-trivial.
Yeah. So but I do think that most of the useful measures could be at least approached by scalable functions. And
I see. So maybe actually.
And some of the definitions could I mean, this would be very strong and probably is not easy. But for instance, if you show that the distillable entanglement is scalable from the definition without calculating explicitly, but you find some way to show that it is scalable, then you just, suppose you show that it is too scalable. And then all you have to do is to calculate numerically for 2 copies, and then check how 4 copies depend on these 2, and then you collect this numeric data, and the rest you know through scalability. But you have to show first.
I see, and it's not easy, right?
No.
So that actually leads to my next question, which is how do you really guess the order of the scalability? for instance, in one of your examples, you've done it by information on that plot, right?
Mm-hmm. Well,
is there a test or something, or you
no.
guess?
I just the two examples that I have is that I just checked it for the L1 norm of coherence. So I checked it, and I found that depends only on one copy. And in the second case was just this pair. I was looking for something. I found that analytical result, and then I was able to show that it is. I realized that it would be impossible to be one scalable. Then I tried the next, and then I saw that it would fit, and that's it. So it is hard. It is indeed hard.
I see.
So I am trying to show this to people that is more talented in mathematics than I am, so that they can have some ideas, and I don't know.
I see. I mean, at least I would say I kind of agree with Lucas that there is more to know about these quantum channel capacities and stuff like that.
Yes.
This may be a new interesting approach to it, you know.
Sorry.
Since it would bring new information to these series of quantum operations and stuff like that.
Yeah. Actually, to give you the maybe you. I mean, if you know how the series converge, you can calculate an upper bound for the breakdown of additivity.
Mm-hmm. Yes.
This would be a very nice result.
Yep.
Yeah.
Yep.
It's not always that scalable functions are regularizable, as you know. But yes, we can try to check the asymptotic behavior and so on. And yes, a theory of scalability for channels would be very interesting.
Exactly. Yes, that's my point. Yeah.
But in any case, we would have to show that it is indeed scalable, or at least can be approached by a scalable function.
But in any way, I would expect this to be even more complicated than for states, talking about channels and stuff. But in some cases, it could be.
Yeah, in fact, I have to tell you that the theory is so general that basically all these results that I am showing to you are valid for channels.
Exactly, and, yes.
Yeah, because you would have to say about the tensor product of channels, but I think that it would be valid, and the challenge would be simply to try to find a way
translate the results, I would say.
Yeah, and to show that the capacity of M channels can be described by a function of a number of real variables. Yes.
That's interesting. Yeah. Anyway, we can keep talking about these.
Yeah, sure.
Yeah.
Do you have a reference about your results on coherences?
Yes, okay.
I think I missed this.
Yes, no, I have. This is the original reference, but there is no mention to coherence here. The paper about coherence is about to be hopefully published, and it is mentioned here. It's. Can you read it?
Not really, but I can. Okay. Oh, that's archive. I love archive.
Yes. And but the last results on one-shot distillable entanglement are not available yet because we are writing the paper. But this is a quite simple paper on one scalable measures, and the example that we give there is coherence. And yes, that's it. So
I mean, I'm asking this because I recently wrote a paper with Łukasz Rudinik from Gdańsk, and I mean, we proposed a case theory for thermodynamics, and the result of this is that each can be interpreted as development of coherency in the energy eigenbasis. So maybe I can apply these things. I mean, it should be interesting to apply these things when the size of the system increases. But I'm thinking about interaction.
But
anyway, how do you put interaction here? If I have any,
it would be a completely new theory. Nothing here applies because then you would have a non-separability developing, and then the reasoning that I presented to derive the condition, the consistence condition, wouldn't wouldn't split things freely. So it would be a completely new theory. So if you have any, idea, you can get to me and we can talk.
Okay, good stuff. Do we have another question? Yeah, Nicholas is thanking you, Fernando, for your talk.
Thank you for being here.
Any other question? If no, I would say we can call it an end for today because Professor Fernando has to leave.
Yeah, it's 11 a.m. already.
Yeah, it's 11 a.m.
Yes.
Okay, so thank you so much, Professor Fernando. Let's keep talking about these. I would say it looks quite interesting, this idea of applying these to channels and trying to gather new information about this stuff. So
okay, I'm happy, and thank you very much for the invitation. And well, see you around.
See you.
Yeah,
Bye bye.